Morgan and Joel, welcome. We are ready to start our 12.2 notes again. We were doing the flopping fish problem. So when we did that, let me review where we were. We had some sort of weight of the fish and some sort of length. And when we did that, the data was curved. Can you point to that curved data? It has to become a problem for you. Yes. All right. So it's there on the front bottom. You have the curved data. Right. All right. So you know what we're talking about. This is a big problem. What are we going to do? So
we're going to cube it.
We're going to learn that sometimes you can take data. Just because they cubed it on this one and it worked, it doesn't have to be. It could be squaring, raised to the fourth, square rooting, fourth rooting. So you could try a lot of different things before you straighten your data. So I'm sorry, but that's true. Luckily, they did the heavy lifting and they just showed us the graph. So the first graph where we did, this is just in general, they cubed the length and it straightened out the data. And then the second way, they took the cube root of the weight and left the length alone, which also straightened out the data. So then we ended class saying, well, which one is the best? We actually, from the mini tab, we had a actual line with an A and B, and we had from the mini tab an actual line with A and B, and we put in what, 36 centimeters, and we came out with two answers from both lines that were fairly close. But at the very end of class, at the grand conclusion, we decided one was a whole lot better than the other. Bree, which one and why? Do you recall?
Oh yes. We said that it was the transformation 2.
All right, this
the one with the 3, yeah.
All right, so why is that one better?
Because it has a better error.
Right, and what were, in fact they were quite different. What was S for this one? You can look on your flap.
It was 18.84.
18! That means you are expecting an error using this regression line of 18. That's plus or minus. And what was it for this one, Bree?
0.12.
All right, so do you see how that's an important number to look for when you're looking at things? Any questions about that? All right, let's pick it up from there. So that was sort of the end of our story yesterday. There are other ways to straighten lines, and they are old friends of ours. I'm so excited. Other ways to straighten lines are logarithms. So,
oh my goodness.
So let me remind you.
Log.
Can you remind me, Maggie, what the base is for an ln logarithm? And what the base is?
Log is 10, right?
Log is base
big
10.
button says
Maddie, what
log.
about ln?
Have it.
Base.
The big button says log.
What?
Base is 0? I don't remember.
Not 0.
It's not 0.
No. Anyone?
Log.
What is the base of an ln logarithm?
Can it be anything?
You cannot go out into
Ryan's right. Ryan's right.
What?
It's something weird like E.
Very good.
Yeah.
Thank you. All right.
Just like
No, base E logarithm is the natural log, and base 10 is the common log. So either one of those can be employed to help you straighten the data. Before we do the example where you see that happening, let me remind you of some log principles. So if you have the log of two things multiplied together, you can rewrite that as two logs separate, but what? So what do I put in between the log of A and the log of B? What do I put in here? Plus. All right. So how's that work when the log is taken of two things that are divided?
Minus.
Thank you. Seemed like yesterday. I could also put the word log in and it will work the same. The third rule,
Put it in front of my
ln of, say, x to the b. You can put it on front, there's plenty of room there. Log ln of x to the b has a special twist to it. Do you recall where else I can put the b?
It's in front.
Down in front. So it can become from a power to an exponent with logarithms, and again, that works also for log. So remind yourselves by writing those rules somewhere. There's still room on the front. That's a good place. Those will be less important. I am going to use those one time, so I want you to know what I'm talking about. But the one that you're going to need is this principle from logland, and that was, say we have ln of y, some number, equals 3.4, just for example. So your equations are going to bear out at the end, the last line, something like that, and you're going to need to get rid of the ln of y. In other words, you're going to have to solve this for y. So in the end, I don't want to know what ln of y equals, I want to know what y equals. And it's that step that you may have forgotten.
Oh, wait,
Do you recall what it is?
Oh, you do something to it.
Is it like to the inverse?
Oh, it's to the -10. To the inverse, yeah.
To the inverse log. Inverse log.
what?
Inverse 10, inverse 10.
No.
Oh, well,
It's
that's
inverse
all.
X inverse?
You raise them both to the e.
Right.
That's
yeah.
right.
All right. Sort
you
of.
do that-
Raise e to those.
Yeah, but
We
you
call
do
it
that by doing the inverse.
exponentiate. We
Yeah,
call it
yeah, yeah.
exponentiate. We
Yeah.
Good job. All right, we're going to make these exponents to e. If this was log, this would be a 10. So I'm just going to show you that. So this leaves you just with y equals and e to the, let me remind you on your calculator, can you do e to the 3.4?
Yeah, this is the inverse.
I think it's above
Second
the ln.
ln.
Go above the ln button and then the screen will
29.96.
I wish you worked right.
29.96.
29.96.
What is it?
29.96.
29.96.
Second.
Staples will be able to fix her.
All right, so once again,
LN.
if this was an
Can you
LOG
see it?
Right there.
that you were, quote, undoing, you would exponentiate it to a 10, not an e. All right.
Wait, if it was a log instead of an ln?
Yeah.
Got it?
All right, does that look familiar? All right, get that down. I'm going to erase it. We'll need it a little bit later, but not right this moment. All right, we're going to look at an example that allows us to straighten data with logarithms, and it's about transistors. So I need a reader about transistors are pieces that fit on a part of the computer called a chip.
Whoa.
And in the beginning, in 1970s, they couldn't miniaturize the transistors very much, but every year they can fit more and more transistors on a computer chip. So we're going to read about that. So Maggie, pick up that story for us.
Sure.
Gordon Moore, one of the founders of Intel Corporation, predicted in 1965 that the number of transistors on an integrated circuit chip would double every 18 months. This is Moore's law, one way to measure the revolution in computing. Here are data on the dates and number of transistors for Intel microprocessors.
Okay.
Like the words open to.
All right, so we're looking at this data, and you can see how rapidly the numbers changed over the years. I can't imagine where we are now. This is 2010, so, all right. Looking at the number of transistors on a chip as time goes by, notice that the years on the graph are marked as years since 1970. And then on the side is the number of transistors. So observe, point to that data and show me that you are with me. Are you finding a weird looking data curve that is certainly not linear? Point to it.
Oh, yes, very much so.
All right, do you see where we are, Kevin?
Yep.
Oh,
Just
All right, where are we?
Show me here, there's no letter
Okay.
K on this page.
Do you see where we are?
Yeah.
No, you don't.
Oh, boy. No, we're on the transistor.
Okay, very good. All right.
My fault.
So this is the data that we are bold enough to try to straighten. So what we're going to do is right here is number of transistors, and down here is years since 1970. So with the similar X and Y axis, I'm going to keep this to be years since 1970, but I'm going to take the ln of the number of transistors. When I do that, can you show me that you're now looking at the new graph? which is, for all purposes, most of the places linear, most of it. So which end, Andrew, is not exactly linear?
Wait, which end?
Yeah, which end, END?
Of the graph.
Yeah.
Okay, sorry, I know, I knew what you were asking, I thought that would like end something that yeah, no, on the right by
Yeah,
40.
sort of kind of takes a little
Yeah.
curl right there,
Yeah.
but this part is fairly linear.
Yeah,
So
everything
they were happy with that. So, question A, if you put a little star there, it asks you, why would it be reasonable to use an exponential model to describe this? So we're going to come back and answer that question in a little bit. So just put a star next to A, and remind me if I don't come back to what we start. But on B, we're ready. Minitab output is right there, and that is transformed data. So do you see the word transformed above the mini tab?
Yes.
Would you circle that? Because it's important to understand that that mini tab is this data with the transformation taken already of ln of the y value, which in this case is number of transistors. All right, so we are supposed to read that mini tab and come up with a least squares regression line. So with your pencil, go ahead next to the mini tab, do part B, see if you can come up with the equation.
Oh, just the okay.
So you're doing part B. We're going to come back to A another day, hopefully today, but not right now. Can you come up, before I even taught this,
Yeah,
with the regression line? So you have to read the mini tab. It's amazing, when we first looked at our mini tab, we knew what like 1 or 2 numbers are. And now I look at this and I think I know what they all are. Shocker. All right, so Ryan, you want to get us started on this?
Okay. B is 0.36583.
Okay. All right, so that goes in front of our x value. So what will go over here? What else do we need, Ryan?
0.01048.
Where's that?
Wait,
No,
that's
that's
what I got.
standard error. Well, we don't want to mess with that unless we are trying to do a confidence interval or something, which we're not.
34.91.
What's that?
34.91.
34.
that's
yeah.
the
Do we want 7.06?
Yeah, what you're looking for is A, Ryan, and A is always across from the word constant. So this is what we're looking for A, and that's B. This is for when we're doing tests and confidence intervals.
7.0647.
Right, all right, you got it. 7.064, you see where these numbers are coming from? And
Wait,
this is a plus.
I was on the same like train as Ryan, so it's not.
Well, it's the wrong train, get off.
Wait, it's A plus BX.
Yeah,
Take a roll.
Why isn't it the one across from it? Because that's what we've been doing.
but that's standard error.
Yeah, but that's what we did for the last few ones.
So you're looking
Number
for
eight.
the ambulance.
No, the ones we did a few days ago, we just moved over across one, and that was.
That was
The
the
net-
standard error.
You have to look and show me, because A and B have always been right there. All right, A is your constant, and B is the one that takes on
Yeah,
another
for confidence
name.
interval, we did the SE coefficient. It's
Right,
just
we're not doing a confidence interval. We are just coming
Okay,
up
so
with the
it's different for
regression
ones.
line.
It's different for ones that aren't confidence interval.
Yeah, confidence interval is all this stuff. B plus or minus, T star, SE of B.
Okay, so
We're just doing the regression line.
okay.
All right, we're not done with you, Ryan. So, what happens over here? I do not say y equals. What do I say?
Y at.
What?
Okay. Alright.
Because we have transformed this, what do we do? What are we coming up with here?
It's the y cube root of
No.
the cube
Fine
ln.
All right, right.
Would you say
ln. That's the transformation we're using. We're using the ln of the y value. Do you see it on the graph that was straight? Circle it. Circle ln right there. LN. It's not very obvious, but it's there. LN. Did you circle it? You did.
Where's
Alright,
the LN?
It's on the
Got it.
vertical
see
part
it?
of
Got
the
it.
top graph.
And
I
show.
had to change the. I've been writing LM instead of LN.
Alright, so right here is what I'm looking at.
Okay.
And you have it?
Oh,
Alright, yeah, there it is. Okay, so show people in video land. So, you had to look at that graph and see how did they straighten it? What did they change? They took the ln of the y value. And so that shows up in your regression line. So you've got to pick that up from somewhere. And this is expected, so put your hat on. Be polite. Alright, and so let's put in some more meaning. What's the y value? Kevin, instead of y? What would I say instead of y?
If you have a hat
So
nearby,
can I
you have to
more
put it
meaning
on right now.
for this problem? What do I put in for y and x? What do they actually
5 seconds.
stand for in this problem?
LN
transistors.
Two.
Transistors and years.
Kevin? What are we
Yeah,
talking
this
about?
Or that one.
Oh, transistors.
Yeah,
Yeah.
number of transistors basically. Number of transistors that fit on a chip, and then what are we talking about here, Kevin?
We're talking about years. Since
Years, since,
1989.
alright, so here is the regression line. Would you be able to have gotten this part right here? Alright, well that's what I'm training you on, so make sure that you are understanding that. Put that ln in. How did I know it? Because I looked at the top graph, the straight one, and I saw they took the ln of the y value. Alright. Part C, use the model from part B to predict the number of, so here's the model from part B. Use this model to predict the number of transistors on the chip in 2020. So pick up your pencil and see if you can do that.
Wait.
Work quietly.
Can you say that again?
Read C and do it. Down. Part A is on hold. B we just did, we're on C. Alright, ignore me if you know what you're doing. I noticed that to complete this part, I need to put in here a number, and it is the numbers of years since 1970 to 2020, which looks about 50. Am I right?
Yeah.
Alright. So when I put a 50 there and calculate it all the way out, I need a number, which I will bounce off of the next guy. What you got?
25.36.
25.36, anyone?
Yep. And then we have to do the whatever the
Alright,
LN.
so I don't want to
GE,
know
I think.
what the ln of this number is. I want to know what this number is. So I'm going to exponentiate both sides.
How do you do it again? 50 years. So 50
Yes.
years.
Like
How do you do the x on your calculator?
E11.
I got it.
So
Yeah,
Alright.
1.00000.
A lot. Alright, what did,
I
can
think
you
it's
read
to
your
the-
screen, Haley?
Yeah,
So
so
we
you
have
make both
point-
sides the
it's
power
E.
of E.
Yeah, how do you do it on your
it's
calculator?
point zero
Oh,
zero
second
zero
LN.
zero zero zero
No,
zero
you're
zero
going the
zero
wrong
one.
way. The zeros
should be
are
like
gonna
third-
on the
third
other
above
side.
all.
Oh, it's giant.
Right.
It's like
What?
billions.
It's number of transistors on a chip.
Oh, one. I cannot read that number.
We'll just read the first number, two numbers past the
12
decimals.
zeros.
102.8
1.028 times
I got
10
1.02.
to the 11.
11.
Oh,
Alright,
wait.
wait. I
Alright.
don't know how to do this.
I got 1.023.
I got
Well, if you round, oh, I
I didn't
didn't
round
get
anything. I
Alright,
just
I
put
didn't
it
round
in.
anything.
So it's
Ryan?
102.
You can't get it
I
out
bet
of
your
your
calculator just gave you more decimals for one of them. For like the one before. I don't
Yeah,
know.
maybe.
I got 1.0.
Because I just took the answer.
Yeah,
I
you
got
wrote
1.028.
you wrote
Me too, right?
.06 I put 06,
Oh.
07.
Listen, you know what it is? Because Haley and I probably put it in
okay.
as 25.3562, which
Yeah,
is the
it'll
whole
make a
thing, instead of
difference.
25.36.
Yeah, I put in the
Okay.
7.0647.
What
Okay.
We should
Yeah.
round it off.
0.028?
Yeah.
Okay, the smallest change when you're doing an
What do you
exponent
mean when you do it?
makes a big difference, but I will accept all of those. All right, Brian, did you find where to put it
That's
in?
cool. Yes, I
So
did.
it's 102.8.
How about you, Andrew?
Yeah, I got 1.028.
But you found where to put it in your
Yeah.
calculator? All right, other questions? All right, part D. A residual plot is drawn for you there. So discuss that residual plot. Does that look like it's a good liner or not so good? Shannon, what do you think?
I mean, it's not great.
No,
Fails
it's not
N.
good.
It
No,
looks
trash.
awful.
And what's trashy about it,
Looks like a
Maddie?
good roller
It
coaster
doesn't,
though.
like, there's not an equal amount on both sides.
Above the line and
Yeah.
below
It
the
would fail
line.
N.
The only thing I will say in its favor is we're talking about these huge numbers, and look at the residual. Looking at the scale of the residual.
Oh yeah, it's tiny.
What's the scale that you see there? Dan, do you see what graph I'm looking at?
Yeah, it's
So what's
negative
the
1 to
highest? The dot that goes up the highest is
1.
1. So we're talking about a residual, a plus or minus, an error of 1, when we're talking about numbers this big. So what's the lowest number, Dan, that looks like
Negative 1.
a little below, maybe that,
And
negative
not that,
1.2 or
There's
something?
8 on top and 8 on bottom.
Oh yeah,
That's
then that's
true.
good.
That's true.
It seems to
So even though the spread is not great, and I don't think there's equal variance across, we still continue because the residuals are so tiny compared to what we're looking at. So that I wouldn't have picked that out without help from the book. So I'm just giving you an arsenal of things to look for.
Wait, so
Yeah.
Arsenal.
So you
Okay.
would pass it?
Pardon?
You would pass it?
Because the residuals were tiny. All right, we'll come back to A in a bit. So keep that under your hat, and we're going to go on. All right, I am assigning you the next one for assignment later. So it's about population. Is that right?
Yeah, the next one's about population.
Population. So you're going to do everything that we did together again.
So it's,
All right, so let's go on to the next one where we're looking at a planet.
wait, is that 2, 3, and 4 then?
All right. Let's see how far we can get on the planet. I'm not going to read all the blab about the planet. I'm just going to tell you about it. It turns out, as we look at planets, we evaluate their distance in AUs. AUs is the distance, 1 AU is the distance from the sun to the Earth. So if you're looking at Neptune, it's about 30-some AUs away from
The
the
distance
sun.
of the Earth to the Sun is always changing though.
Well, the average difference. So AU. And so the AU is going to be the average distance that the Earth is from the sun. So we're going to evaluate all the planets in relation to their distance from the sun in AUs. And then we're going to compare it to their period, which is their 1 year. Period is once around, a cycle. So in other words, their year. Okay. So there in the list are the AUs for all the planets and then their periods in years. So from that, we are supposed to look at the data. Notice the original data is supposed to look like little planets there. Didn't show up on the copy so much. It almost looks linear, but it is curved. Would you take your pencil
These are the
and
planets.
draw a curve on this graph to show me that you are aware that if we graph period to distance, we do get a curved graph. It doesn't look too curved until you actually put the pencil work in. All right?
It's just curved a little bit.
Okay.
Just a little curve.
Yeah, it is curved. All right. All right. So now, in their first attempt to straighten it, Look below, on the graph to the left below. Shannon, what did they do to attempt to straighten it?
They did LN.
All right, they took the ln of the y value just like the transistors, but guess what? It's still curved.
Oh,
So
no.
draw it again, draw a curve through that. That is really curved. So we had an epic fail there. But what did they do on the next graph? Ryan, observe that and tell me what they did to straighten it out.
They did an ln they did the ln of the distance.
They what?
And they did ln of both of them.
They did. All right, circle that. Circle that so I can see you are following.
So there's 3 ways now to make it.
Yeah, would
straight.
you go over those 3 ways?
Sure. You can cube root it, cube it, or ln it.
Right. You can ln1 or you can ln both. Or log,
But you can't-
and it
you
doesn't
can't-
have to be cubed, it'd be to the 4th or the 5th.
It's the original
You can't
line,
cube it,
got a little bit of curve.
cube
All
it,
right.
and then we
Alright.
tried to cube it, we tried to ln it on that
You're
side
not what?
there,
Take the tangent of it.
and it's still curved. And then we
Alright,
took the
let's turn over and
ln
look
of
at
both
the
sides,
regression
the y and the
mini
x,
tab.
and
And
it's
see if you can come up
I do
with the
those
model, the
between the
LR,
dots.
the linear regression line, the least squares linear regression line, looking at the fact that it took 2 logarithms to straighten it. And see if you can come up with the mini tab to come up with the regression line that reflects that both x and y were taken the ln of.
Wait, make a mini tab for.
No. She did spoke.
We're doing B. B again.
I don't think we'll ever have to make a mini.
Oh, use the mini tab.
I would.
Right, use the mini tab.
I was sorry, I was looking.
I think I have.
You think you got it? All right, Maddie, read off your regression line.
We're doing
So
one
we're
on the
doing
back,
part
right?
B on the back for the planets.
Okay.
All right, go ahead.
So I have LNY
All right.
equals 0.00025.
0.002544. Yeah.
Yeah. Plus 1.49986 lnx.
1.4986 ln of x.
49986. Yeah, you got
Another
it.
9.
Yeah, no, that's right.
499.
That's an extra 9.
It was right.
All right. I had it right before.
I wasn't
Yeah,
looking. I just heard her
All
say
right,
one of the
got
9, so I.
Okay. All right, now the only thing I want you to improve on Maddie's model is to put in some meaning for x and y. Shannon, step up to the plate. ln of what?
So you have to do the ln of period
Right.
equals that number plus the ln of that number times distance.
All right. All right. So we'll pick that up tomorrow, and your job is to do everything, unless it asks something about exponential models. Let me see if it does. All right, on your homework one, you can skip number 1. What you're going to do, number 1 talks about things that you're going to put a star next to. We'll come back and finish that tomorrow. So you're going to answer 2, 3, and 4 on the population problem.
Wait, what's called?
This one.
It is this one.
The one that we skipped.
Okay.
And we're not doing number 1. All right, can you show them in video
Yeah.
land? Okay. And then you
Thank you,
can
guys.
All right.
So this is the given table.
It was so fun. Oh my gosh.
That's the given table for the problem.
Edgewood was the away team, and the Edgewood coach is
Pause if you need it. And there are the graphs, some more
I hate
words.
that. When they act like they
You know what you're looking at. I don't know why I'm explaining it.
2-year-olds.
Mini tab.
Like the first thing he
There's
said
some
to me
more
was,
stuff.
he came up to me and was like, so I
Yeah, boy.
playing my guys been out here 5 or 6
Nope,
years.
that's not it.
Yeah, and he's like, I'm gonna
the
put some of
homework
my
is
slower
these
pictures in because I'm
2,
scare
3,
the
and
crap
4.
out of the
That's
other
the
kids.
homework.
I was like,
We don't have to do 1.
I can't pay you, right? You play your game, you play their game.
So where was the
First try, watch.
period?
Yeah, first try.